All right, hey everyone. I'm really delighted to be here. My name is Jill. I'm from Germany, Munich. And for the last 5 years, I've been working on machine learning problems coming from electrical engineering for low-level hardware devices like microcontrollers and FPGAs. And today I want to share a couple of thoughts and a couple of insights how designing machine learning for the cloud is different from designing machine learning algorithms for those devices. All right, let's jump right into it. So AI today is, of course, solving many problems, right? We've heard many talks the last couple of days, and a lot of companies are doing stuff without us even knowing, and it's definitely affected our lives. And the kind of development was that first people tried to decode or basically make certain fundamental things possible. For example, that it's even possible to detect a cat in a picture. And then once that worked, it was about gaining more area under curve, getting more higher accuracy. And then in the end, you're educating your customers to actually use these services because AI services are still kind of new. And most of the time, these models are trained offline. You have a certain fixed data set, you train it, you make sure it works, and you deploy it. And for me as an electrical engineer, most of the time this happens pretty much free of constraints. So people developing AI stuff at companies like Google, maybe not in the latest stage, but in early stages, they know I have a huge server farm, and it doesn't really matter whether the algorithm takes 10 microseconds or a second, because the latency, no real time, basically is not so important. And how is that different for real-time autonomous systems? So first, I'm going to talk about what kind of constraints developers in real-time autonomous systems are facing. Next, what you can do to unlock use cases which seem impossible, but may not be impossible. And finally, talking a little bit about the frameworks and the frameworks that are available and what are the problems with it, and also the kind of people that companies might want to hire but are not really hiring right now. All right, so on the left side, right, we have something in the cloud. So to have a common understanding, it's definitely centralized processing. It's parallelized over many cores. And there's a focus on performance over cost, as I said, at least in the first couple stages. Now, in real-time autonomous systems, definitely decentralized processing, right? You have a certain device, for example, a drone, and it has to do all the processing. It's completely autonomous. So you can't upload stuff to the cloud, wait for it to come back, because that latency would completely ruin your whole use case. And it's optimized heavily for a certain architecture. One time I spent half a year with a colleague optimizing one algorithm with only 180 parameters for an FPGA, and just optimizing it for we even thought of how to store matrices in an FPGA structure. Okay, so it goes that deep to really make it possible and to really gain performance boosts of maybe a factor of 1,000 to 10,000 to actually make it work in such a system. And the focus is definitely on overall feasibility. So an example for the left one would be you have an algorithm, you can upload your holiday pictures, and then the algorithm will tell you you have a smiling, happy dog running on a beach. And on the other hand, you might have something like a drone flying through an unknown area and basically doing what we're doing the whole time when we look at stuff, basically detecting anomalies, something that sticks out. And okay, so what are the hurdles, what are the barriers that for example, engineers like me, electrical engineers, but also PhD AI candidates working on these in this kind of field are facing. The strongest one is definitely power consumption, because it's just basically a combination of all kinds of things: latency, throughput, model size, final accuracy, training speed if you have to train online. And an example would be, let's say you have a drone, and you have 30 amp hours of battery power, which is a lot for such a device. And let's say you have 200 milliamps of peak power consumption in the system, which is reasonable for a hardcore optimized electronics embedded device. And if you do the math, you have 5 days of autonomous flight with that drone, okay, just doing some simple stuff on a tiny microcontroller. What if your customer wants 10 days or 20 days? How do you do that? Do you have to throw away 50% of all your weights, of all your synapses in your neural network? That could happen. Or you have to hardcore optimize. You have to maybe substitute the controller for something else. But in the case of Reality AI, as we heard today, sometimes you just have to work with whatever you get. Next, the training speed. We heard about Adam, for example, before. Gradient methods are great at a lot of things. They probably evolved because neural networks are nonlinear systems, so you can't use linear equation system solvers. And they're great at a lot of things, but they're not so great when it comes to like really optimizing for a dynamic channel. And by channel, I mean basically the weight vector that you're aiming. So when you have to train for let's say noise cancellation, like active noise cancellation, like your smartphone does or your noise cancellation headphones do, you basically have to constantly train after the model that you have to find. And there, other optimizers might make sense. For example, optimizers that only solve the weights which right now contribute the most to the current error. And finally, determinism is definitely important for a lot of entities when you're like in a startup doing machine learning stuff. Like you have to convince your customers that whatever you do, they could somehow still understand. And especially if you want to put a real-time autonomous system out on the market, very often it's going to be a safety-critical system, like a robot interacting with a human hand or industrial tools, both sometimes at the same time maybe. So you're going to have to prove to institutions like TÜV that your product is safe. And how do you do that if you have a very deep neural network? You might have to really make your model simpler. For example, going from a recurrent model to a non-recurrent model. This is what I experienced once. So let's say you have a drone. Let's do a little example here. So I mentioned that before you have a drone with a camera, let's say 60 frames per second, which is a decent rate if you're flying at maybe 50 kilometers per hour. And let's say you already condensed it down to only 100 times 100 pixels. And you have no colors, and you're using some kind of convolutional neural network-based autoencoder like Mr. Prabhat from Berkeley presented as well. And just a rough estimation would result in 48 billion floating point operations per second that you would need for such a use case. And I mean, this could be like a base layer for some kind of visual detection of objects of an autonomous drone in the future. Okay, if you look at the market for embedded hardware, you have stuff that you can easily program in C code, like state-of-the-art embedded controllers like the PIC32MZ that I've been working on for quite some time. And but as you can see, like it would not nearly be able to process that kind of stuff. Not even a very like I think this processor is from the Galaxy S7. And even this one is not being able to do something like that. And we're not even talking about the power consumption of a 100% workload ARM core in a smartphone. And as you can see, the price point is also pretty high. Then you have stuff that is a bit harder, or actually a lot harder to program, like FPGAs. They do have a lot of power and come at a reasonable price, but the power consumption is also pretty high. And especially you have to work with integer or fixed point numbers instead of floating point numbers, and that requires like it opens up a completely new world of optimizing your algorithm. And then finally, you might have something like GPUs, even in smartphones, which have a tremendous amount of power, but again, power consumption really high. And well, coding in OpenCL or something, you know, who can really do that? You have to train your people. So basically, there's still many use cases that are unlocked. Now, what can you do if you want to optimize your algorithm for such a platform? Let's say you have these 4 goals, okay? You want to decrease the number of operations. You want to increase the training speed because you have something that you have to train online. You want to really understand and exploit the underlying architecture. And you want to improve the clarity for, well, your third parties. Okay, so the first thing you might think about is, okay, I have activation functions. Activation functions are mostly have some kind of exponential function and are really hard to compute for a microcontroller. They're very expensive. For some time, convolutional neural networks, or even still now, for example, have been using rectified linear units, which are completely linear. But even these are now moving to exponential linear units. So because smooth functions make more sense, they have better mathematical properties. And however, they're very expensive, as I mentioned, and it also narrows down, because it's nonlinear, to certain kinds of solvers, right? So for example, gradient methods, but not linear equation solvers. And what can you do? Well, you remove nonlinearities through segmentational linearization. I'm going to show a plot just in a second. Other things you can do, recursive pruning. Yeah, like you have a network with 10,000 parameters, and you're somehow through regularization you're able to tell, okay, actually I only need 1,000 parameters, but it's like random synapses that I can get rid of. Like I don't know any high-level framework that can actually like recursively, iteratively do that like out of the box. And especially not frameworks that could potentially create C code that you can directly deploy on microcontrollers. Another thing is weight quantization, also something that you can hugely benefit from in terms of performance, but again, no common frameworks really offer that out of the box, like frameworks like Keras and Python, for example. Or completely other crazy things like synapses that go over certain layers and so on. And this is basically one of the ideas, right? And this idea is basically from a paper that is like ages old, and people, like this kind of linearization is not even available in current frameworks. Like, there's hard sigmoid, for example, but it has like 3 linear regions, and that's it. All right. The next thing is training speed. Like, let's say you've linearized your network with the previous step. Then you're able to go from gradient methods to, for example, linear equation system solvers, which allow you to design them in such a way that you only solve the weights first, which contribute to the error the most. So it's a really nice thing for example, noise cancellation, where you have a smartphone and you walk around the whole time. The channel changes the whole time. The reflections of the sound change the whole time, and you have to constantly learn. So they're much faster and fundamentally more powerful. But now you might think, okay, if I solve a linear equation system, I have to invert a matrix, which has cubic complexity. But especially for time series problems, you can exploit a lot of the data characteristics to make it to linear complexity. So it is possible. And you can really gain a lot. And here, for example, you can see what we're talking about, like really orders of magnitude. Here you see an adaptive filter trained one time with LMS, which is a gradient method, and RLS, which goes more into the direction of solving a linear equation system. And you can really see that it's much faster and much stabler, because it just solves an equation and doesn't go down some optimization map. And the third thing would be, you have to ask yourself a couple of questions. If you want to optimize for a certain platform, how many bits does each weight need? Can you work with integer numbers? Do you have dedicated digital signal processing components in your microcontroller that you can exploit? Can you use an FPGA, or do you have to use some kind of general purpose processor? And if you really exploit that, like I've seen it in projects, you can just like boost your performance by 1,000 or 10,000 times. It's really a completely different thing that opens up suddenly. And you can even make work, like even convolutional neural networks could suddenly work on a microcontroller this big. But the kind of knowledge that you need for that is mainly in the field of electrical engineers, and those are still not very often being hired by ML departments, because people tend to think that having knowledge in AI is more important than having knowledge in the field that you're working in, or the platform that you have to deploy it on. And then there are, of course, always papers like telling, okay, now we gained another 5% AUC, but we went from a model with 10,000 parameters to a model with 4 million parameters. And I, as an electrical engineer, then always think, that's no magic, right? If you put so much more power in it, it's no wonder, like it would be actually a bad thing if no higher accuracy came out of it. And then finally, you want to improve the clarity of your algorithm. So I'm just going to skip a couple of things because the time runs out. What you might have to do is... all right. So let's say you have a very deep recurrent and nonlinear model, like an LSTM. It's really hard for like someone at a certain institution who wants to approve your product for the market to understand that, right? Very often they don't have the knowledge, they don't have the expertise, and even if they would be right that even the developer doesn't understand anymore what this thing does. But in some, and especially like if you do, for example, sensor fusion for a car or a plane, it is really safety critical. Like people can die if you don't know what your algorithm will do at all times. So what you might have to do is you have to as I already mentioned, substitute nonlinear functions by linear ones, removing recurrences, and make the model a bit shallower. And for example, if you would go to such an institution and tell them, I'm using a digital filter, they would be like, okay, yeah, that has been done for like the last couple decades, it's fine, like we understand that. If you tell them, I'm using a one hidden layer, a time series convolutional neural network with linear activation functions, which is exactly the same thing, they would be like, oh, wow, no, okay, this is some new shit that we don't know about, and you have to make this simpler. Yeah? So it's even about phrasing the things. And especially also towards customers who first do not really trust your neural network magic. And then you can use classic methods like from digital filters, like show them some diagrams, what kind of frequencies are being filtered out. All right, so frameworks. There are many tools out there, right? And there are some high-level frameworks like Keras, and there's some low-level stuff like MATLAB. MATLAB, for example, is able to train a neural network, automatically convert it to C code, and deploy it on a microcontroller right away. This is awesome. This is awesome for sensor companies and all that, all these companies in all these areas. But they're very out of date. They're still using gradient methods, which are completely outdated. And the more up-to-date ones, well, they cannot convert it to C code, right? How do you convert Python to C code using Cython maybe, but it's a mess. And so you have to kind of bridge that. You have to have people in your company who are kind of bridging that, who, for example, electrical engineers who are still trained in using higher level frameworks so that they know what's going on in the market and then are able to maybe code that in C code themselves. And now one of the most important things I think in companies wanting to develop machine learning for real-time autonomous systems, AI is considered as a tool, which I think is a good thing. It's fair enough. And then you have PhD candidates, right? Like, I don't know, people coming out of Cambridge who did a PhD in activation functions, and they're like the AI cracks, and very often companies want to hire them. And those are AI students, I would say. And then there are other guys like, I don't know, biologists or physicists who have great field knowledge and are really using AI as a tool. So they're more like an AI teacher. So you really have to ask yourself, do you want the teachers or the students? And an electrical engineer, in my opinion, can, like, you give them some months on Coursera, you give them a couple of trainings in statistics, and he will basically quickly understand the basic concepts of machine learning. While an AI PhD candidate might need like years, obviously, to understand the math around robot arm control or wireless protocols or the architecture of an FPGA. And one really interesting thing is that in the last company where I worked, some of the most brilliant ideas of how to solve our problems that we've been working on for maybe over a year, have come from mechanical engineers who had no experience in programming, no experience in statistics, but because I spent so many meetings just being a pain in the ass to them and explaining them we need to do neural networks, at some point they understood the concept of it. I mean, supervised learning is a pretty basic concept, and everyone can get it. And they then had great ideas. And then I understood what they meant, and they were like, can we do that? And then me and my team executed it. And so I think it's really vital, and I think it's not being done enough, that you include completely non-AI people into discussions how to solve the problems with AI. All right, in a nutshell again, just 3 points. There are constraints, and you have to solve them with cross-domain efforts. Improvements with a few orders of magnitude are definitely possible. And as a company, rethink what kind of people you want to hire. Thank you very much. I'm going to leave you with a couple of quotes from Silicon Valley people. Basically about that constraints are not a bad thing, but a good thing. Thanks.